everyone, my name is Hannah. I'm from the Asperguzic Research Group as well as the Pot of Computing. And today, as part of my QHack talk, I thought I'd spend some time discussing how to optimize parameterized quantum circuits that have lots of parameters. And so before getting into the details, I thought I'd start off by talking a bit about variational quantum algorithms or VQAs. And so VQAs are a type of hybrid quantum classical algorithms, which means that you're allocating tasks to both quantum and classical compute resources in order to achieve a larger computational task. And so on the quantum computer, you'd be preparing and measuring relevant quantum states that are generated by the so-called parameterized quantum circuits. And once you obtain enough measurement data, as well as the parameter settings of your quantum circuit, these information are then fed into the classical computer where you're doing some sort of parameter update or optimization. And once you obtain these updated parameters, these are fed back into the quantum circuit and you repeat the cycle over and over again up until some convergence criteria. And so an example of a variational quantum algorithm is the variational quantum eigensolver or VQE that tries to estimate the ground state energies of quantum systems. And so if you're interested in learning more about variational quantum algorithms in general, as well as the different applications of VQAs, I suggest these two recent comprehensive review articles on variational algorithms. But today in this talk, I'll focus mostly on parameterized quantum circuits or PQCs, which you could think of as a specific type of quantum circuits where at least one of the gates in the quantum circuit is tunable or parameterized. So if you look at this quantum circuit right here, the vector of parameters are the tunable knobs that you can play around with in order to generate some interesting quantum states using your circuit. And so these PQCs are sometimes called variational circuits or quantum neural networks, depending on the application of interest. And it's been shown that how you design and structure these circuits, as well as how you tune the parameters of these PQCs, are crucial to the overall performance of your algorithm. And specifically in the near term, two things that you want to minimize are the circuit depth, which is you can think of as the number of time steps it takes for your circuit to execute, assuming that some gates that act on disjoint qubits or different qubits can be implemented in parallel, like the ones that are shown by these orange gates here and these two qubit gates here. And another thing that you want to minimize in quantum circuits in the near term is the gate count, because with each gate that you implement, this accrues some noise, and in the near term, you want to minimize the level of noise in your circuit in order to have a reliable computation. So you want to minimize the number of gate operations. And so I wanted to talk a bit about the structure of quantum circuits that people have developed over the years, specifically in applications like quantum chemistry. You might have heard of the famous unitary coupled cluster circuits, which are inspired by the coupled cluster approaches that were applied in quantum chemistry and computational chemistry fields. So unitary coupled cluster circuits or UCC type circuits were shown to be effective for estimating the ground state energies of particular quantum systems, but main downside of UCC type circuits is that this corresponds to circuits of very high circuit depth, which is not favorable for the near term quantum applications. And so in the hopes of developing circuits that are just as capable or expressive as unitary coupled cluster circuits, but have significantly lower circuit depths, there have been various circuit alternatives that have been proposed. And an example of those is the so-called low depth circuit ansatz or LDCA. And today we'll be talking mostly about LDCA because it is an example of a circuit that has significantly lower circuit depth than UCC type circuits, but this comes at the price of having lots of parameters that you have to tune. But before that, I wanted to mention that in applications in, for example, quantum machine learning, the circuits that we employ are a little less structured. For example, what you're doing is usually taking a predefined circuit template, like the ones that are shown in the penny lane page, and you take your favorite set of gates and you populate these gate slots with your favorite gates in order to, in the hopes of generating a effective and expressive circuit. And so today, like I mentioned before, I'll consider the low depth circuit onslaughts, or LDCA, as a case study because of the compact depth, but also the high number of parameters that comes with it. And so specifically, the circuit depth scales linearly in the number of qubits, but it scales quadratically in the number of qubits in terms of the number of parameters. So if you look at the structure of LDCA on the left, you see that it has a very compact but nested structure where there's some levels of what are called superlayers, and each superlayer has several sublayers, and each sublayer then has a series of nearest neighbor 2-qubit operations, each of them shown in a pink block, where each pink block corresponds to 5 different 2-qubit entangling operations, where there are 3 free parameters per pink block. And so as an example, if you were to take a 12-qubit LDCA circuit with 5 of these super layers, this already corresponds to 1,002 parameters that you have to tune. And to compare that, in the case of the unitary coupled cluster circuit, estimating the ground state energy of lithium hydride, a 12-qubit problem, this corresponds to a circuit that only has 56 parameters in comparison. And so you may be wondering, well, then why would anyone want to implement this LDCA circuit over this UCC type circuit? And the reason is because this UCC type circuit, even though it has 56 parameters, this circuit corresponds to a much higher circuit depth than the 1,002 parameter LDCA circuit. And so there seems to be this tension or trade-off between having a high circuit depth or having a high parameter count, where circuits like UCC type circuits have high circuit depth, which corresponds to you're going to run into a lot of difficulty in implementation of these circuits on near-term devices. However, on the other hand, for circuits like LDCA with a high parameter count, this corresponds to running into difficulties in the optimization of circuit parameters. But today I'll be focusing on circuits on this end of the spectrum, like LDCA, where you have high parameter counts because optimization is mainly allocated to classical computers. So you could think of this as more of a classical overhead versus having a high circuit depth, which would require a lot of quantum resources and high quality quantum resources, which I argue is a more expensive resource at this point in quantum computing. And so before going deeper into how to optimize circuits like LDCA, I wanted to talk a bit about the progress that the quantum computing community has made in terms of the optimization of PQCs, where I'd argue that a lot of work has been done in order to improve this step, ranging from analyzing the trainability of quantum circuits to developing optimizers that are tailored for variational algorithms, higher level strategies, parameter initialization methods to avoid the barren plateau problem, as well as running comprehensive benchmarks. But despite all this progress, I want to argue that optimization of PQCs is still very challenging. And it's because what we want in the near term is we want a low depth ansatz that is able to accurately describe some quantum system of interest, but the optimization task itself should be relatively easy. And so with this really challenging goal that we want in the near term, since this is a bit ambitious, I thought I'd narrow down the research question into a particular set of prime choice quantum circuits, specifically circuits that have lots of parameters. And this is because I noted 2 things about current PQCs, which is that, number 1, past studies have developed powerful PQCs, but their applications have so far been limited by the large number of parameters and the corresponding difficulty in optimization, an example being circuits like LDCA. And number two, the way that we're currently designing circuits, for example, by placing single qubit gates on every qubit, followed by some pattern of entangling operations, and repeating that over and over again in a layering scheme, well, this design principle leads to sufficiently expressive, but also parameter heavy and redundant circuits. And so by noting these two observations, uh, my questions were, can we somehow make better use of these circuits by optimizing them more effectively? And so to approach that, before approaching that question, I wanted to go over the way that we're traditionally optimizing PQCs. And so if we suppose that this is the parameterized quantum circuit that we want to optimize, where each of these gates that are in green represents a parameterized operation, what we would normally do is, for example, if we were to look at the optimization, uh, a particular optimization run from the parameter space, the path would look something like this, where each point in the path corresponds to an algorithm tuning every angle or parameter in your circuit. And the hope is that you would terminate your algorithm within some solution representation, where maybe at that point you can do some post-optimization analysis or reduction in order to simplify your circuit and represent your circuit with fewer gate operations and circuit depth. And so while this optimization approach may work for smaller circuits, as the number of parameters increases, the optimizer might be overburdened by the vast parameter space and may spend a lot of function calls just to sufficiently explore that space. And so instead, what we present is what we call parameter efficient circuit training, or PECT, where instead of trying to tackle that large optimization task all at once by tuning every parameter, you instead launch a sequence of smaller optimizations, with each optimization iteration tuning a parameter subset and refining and updating that subset. And again, this approach, the idea of this approach comes from the fact that the way that we're currently designing circuits, not all the parameters of your circuit are necessarily important to prepare the solution state. So what I mean by a parameter subset is that usually you would have a parameter vector that includes from parameter 1 to parameter n, but you're only choosing a subset of that entire set of parameters. So for example, if you have this parameter subset, this would correspond to a circuit substructure that only activates the parameters that are present in this subset. So for example, theta 2 isn't here, so you never apply theta 2 in your circuit substructure. And I wanted to mention that the update and the update mechanism of the parameter subset was actually adapted from classical machine literature that worked on efficiently training deep neural networks. And we'll later show why we chose this particular work in order to effectively optimize parameterized quantum circuits. And so before getting into the algorithm, I thought I'd go over two of the big assumptions that we make in before applying PECT, which is that number one, the parameterized quantum circuit that we want to optimize, we assume that this can express the solution state, but is also prunable, which means that it contains gates that are not necessary to achieve the objective. And this is what allows us to optimize parameter subsets. And number two, the parameterized quantum circuit of interest contains gates, parameterized gates, such that setting their parameter values to 0 corresponds to the trivial or the identity operation. And this is what allows us to do some type of magnitude-based pruning or removal of gates with small parameters. So for example, if you took the rotational X gate and set this theta to 0, you would see that this is the identity gate, which acts trivially on a quantum state. And so this corresponds to, for example, the empty wire in a quantum circuit. And so in PECT, the input of the algorithm is the PQC that you want to optimize. And this would ideally be a heavily parameterized redundant circuit. But for this small example, we suppose that we have 48 parameters. And so in the first phase of PECT, which I call the circuit tuning phase, you choose a parameter subset, which can be done randomly from your circuit structure. And then, so this particular subset uses 33 out of 48 parameters. And then you're going to tune the 33 parameters using your favorite optimizer, which is similar to just your standard VQE procedure. So following that phase, you now enter the reparameterization phase, where first you're going to look at the optimized parameter values of your circuit substructure and prune or remove parameters with values that have close to 0. So for example, supposing that these 5 gates in red were the parameterized gates with values that are close to 0, we're going to remove those 5 gates from the substructure. And then you're going to now add back free parameters in order to keep the parameter subset size constant. So because we remove 5, we're going to add back 5 parameterized gates from these free slots of gates where the gates in the first subset wasn't activated. So for example, we chose these particular 5 gates shown in dark green in order to kind of add back to this parameter subset. So at this point, the parameters count should still be at 33. And so to make this clearer, the output of this process should look something like this, where again, the gates of the darker green color are activated as part of your new circuit substructure, while these red gates that we were going to prune are now removed from the circuit substructure, and with an effective parameter count of 33 by the end of this reparameterization phase. And after that, we're going to repeat this tuning and reparameterization phase over and over again until some termination criteria are satisfied. And examples of these termination criteria may be some convergence in the energies, or you set a hard limit on the number of total function calls that you allow in the overall optimization procedure. And so with this summary of PECT, I wanted to highlight what PECT is doing again, which is taking the large optimization task, and instead of trying to tackle it all at once by optimizing all the parameters, you're going to split this task into smaller optimization tasks. And by doing the reparameterization or update of the parameter subset, what you're doing is adaptively finding an effective parameter subset or the circuit substructure that leads to a better candidate for the minimum or maximum of your objective function. And so if the input of your PECT algorithm was the parameterized quantum circuit that you wanted to optimize, by the end of PECT, the output should be the parameterized quantum circuit with optimized parameters, but also with reduced circuit resources, because you're only optimizing a parameter subset at any given point, and that corresponds to circuit substructures with fewer gate operations than the full circuit, as well as potentially lower circuit depth. And so going back to trying to visualize the optimization run in the parameter space, if your traditional way of optimizing was shown in black right here, where at each point of the path, you're having to execute the entire circuit, in PECT, you're essentially hopping through different sparse parameterizations of your original circuit structure, where at each point in the optimization, you're only executing a partial structure or a fraction of the gates that you had in your original circuit. And this clearly shows why we adapted this particular method from classical machine learning, because of the additional benefit of reducing circuit resources at every point in the optimization. And so to demonstrate PECT, we consider the variational quantum Eigensolver algorithm, where the system of interest is lithium hydride and the minimal basis. This corresponds to a 12-qubit VQE problem. And we're going to consider the LDCA circuit, which I mentioned before, at around 5 to 6 super layers should correspond to about 1,002 to 1,200 parameters that we have to optimize. And so to track the performance, we'll compute the energy error at the end, as well as the final circuit depth and the number of total function evaluations that it took throughout the entire optimization procedure to get a sense of how expensive this computation is. And so I'll break this plot down for you guys, where at first, let's just focus on the PECT calculations. So when I was describing PECT during the circuit tuning phase, what you would do is choose a circuit subset and optimize it using your favorite optimizer. So you have some flexibility in the choice of optimizer. So in this run, I chose the LBF-GSB optimizer as well as the SLSQP optimizer. And you see that the choice of optimizer really matters here, because using SLSQP, you get much better energy errors where they all fall beneath this region of which we call a chemical accuracy, and you want to be below this shaded region. And using SLSQP in orange, you can see that all points in the along the potential energy surface, you're able to get accurate energies. Whereas if you were to use the LBF-GSB optimizer, there are particular bond lengths where the final energies never make it below the threshold. And if you now look at the number of function calls, using SLSQP is also advantageous in terms of reducing the number of total calls that you have to make to the quantum computer in order for the optimization procedure to converge. But then let's just now also look at how optimizing LDCA goes without PECT, which is now shown in blue, where you just use the SLSQP optimizer on the entire LDCA. So in this case, you're trying to optimize 1,000 or 1,200 parameters all at once. And you see that for most of the bond lengths, the energy accuracy is not so great. And also, if you were to look at the circuit depth, you trying to optimize the full circuit at any point corresponds to a high circuit depth, but using PECT approaches, you save a lot in the circuit depth. Also, the number of function calls is very expensive because you're trying to navigate that vast parameter space. And so one big takeaway of this slide is, I think, circuits like LDCA is very hard to optimize without PECT. And alternatively, another way of saying that is PECT may be a necessary tool for optimizing circuits like LDCA. And so to make sure that these great results we obtained using PECT wasn't just out of pure luck, I took 3 different bond lengths in the potential energy surface. And for each point, we ran 25 independent optimization runs to make sure a lot of these points or a lot of these runs can achieve energies below chemical accuracy. And so if we look at the plots right here, the optimization runs that end in these green dots imply that the final energies fell below chemical accuracy. And you see that for all 3 bond lengths, a good percentage of them actually do make it to this, below this threshold. And so what this shows is that PECT shows robustness against parameter initialization for circuits like PECT, but also another way of viewing this analysis is that this reveals the degree of redundancy of circuits like LDCA, where, for example, if you were to look at the compositions of the parameter subsets of these successful runs, the subsets all differ from one another, which means that there are many ways that you can tune LDCA in order to get a good solution candidate. And so to summarize what we were discussing here, I want to say that PECT is a method that's well suited for optimizing redundant and parameter-heavy prime-choice quantum circuits, where specifically PECT enabled optimization of circuits like LDCA, where their application was previously limited by the optimization task. And also it can optimize PQCs with hundreds and thousands of parameters while also reducing on-circuit resources. And so, from the last slide, by rerunning optimization runs many times for a given circuit using PECT, if these runs are successful or high ratio of them are, this can provide additional insight into the degree of redundancies of PQCs. But one limitation I'd say of PECT is because you're running a lot of these smaller VQE optimizations, overall this can get quite expensive in the number of total function calls that you make to the quantum computer. And so for some future directions, all the simulations that we showed today were of PECT without noise. But in order to show that PECT is a good method to use even in experiments, we need to test PECT under noise. Also, there was that flexibility of choosing different optimizers. So it'll be great to test different types of optimizers beyond the LBF-GSB and SLSQP. In terms of some open questions, one big question is, all the simulations we showed today were of VQE simulations, but it'll be interesting to see if PECT can help with also quantum machine learning applications, as well as other variational algorithms that involve this optimization step. And lastly, this is particularly interesting to me, where it's a broader question about circuit optimization strategy. So there's been recent work that's that really, such as the one that I show here, that tries to adaptively build and optimize parameterized quantum circuits by adaptively building a gate from scratch. But I wanted to compare that to a method like PECT, where instead of building from scratch, you're now taking a predefined but expressive circuit structure and kind of removing gates from it in order to arrive at the solution. So it's kind of coming from two opposite ends, building from scratch or taking a flexible circuit and cutting down from that circuit structure. So it'll be interesting to see which one is more preferable for building and optimizing circuits. And with that, I wanted to acknowledge my co-authors and note that the work mentioned in this presentation is available as a preprint as well as a paper on quantum science and technology. And so I'd like to thank everyone for listening, and I'd be happy to take any questions. Thank you.
Hannah, yeah, welcome to the studio and live, and thanks for recording the talk, even if you were preparing for your defense. Before anything happens, how did it go? What happened? Are you happy? Are you just like in this black hole that we were talking about earlier backstage a bit, or what's your mood today?
Yeah, so first of all, there's construction going on in the background, so I apologize in advance if you hear any loud noises, but so I don't know, it kind of feels unreal right now. I'm just like, did I actually do a defense? I don't feel any different, but there is an extra 3 letters after my name. But yeah, it hasn't kicked in yet, really.
Are there recommendations you would have for other people if they are just like basically just before their defense, anything that you thought you should have prepared that you didn't, or was it not that bad after all?
Well, actually, in terms of what I did, so I quit coffee or any caffeinated drinks while I was working on my thesis because I wanted to make sure I got good night's sleep. So that was really nice. And I exercised more, which I never do, in order to really get my brain working. So those two things I would definitely recommend.
Nice.
Yeah.
Okay. So, Dr. Sim, I've got a couple of technical questions actually. So, one of them, okay, let me start one from the chat first. What are the relations? I'm also interested in that actually. What are the relations to dropout regularization? So, just as context in neural networks, you often use as a regularizer, so as a means to make neural networks less expressive, so that they maybe like don't overfit solutions. You just throw away some of the units every now and then in training, so you just like don't optimize parameters. In some sense, this feels similar. So, do you think this could have an additional side effect?
So I think, so for the first part of your question is, when I mentioned that the original work was inspired by a classical machine learning work, I think it was actually, it had contents about dropout and neural network pruning. So that's where I definitely got inspired by the idea. So in that way, so from Amira's talk today, she was mentioning this idea of quantum expressibility. So that was my previous work where I noted that a lot of the circuits that we were designing these days is highly expressive, just following the way of adding single qubit rotations on every qubit, followed by layers of entanglers and repeating that over L layers. So then she also mentioned that that's sometimes not great for trainability because that leads to barren plateaus in the landscape. So from that fact, I thought maybe this pruning or this dropout method from classical machine learning can be a way to tailor circuits so that they become increasingly more system specific or problem specific.
Okay, yeah, no, that's definitely a good one. One question more from myself. So I have to admit that recently I was coding up a Penny Lane tutorial, and sometimes when you code things and you just plot them, you see a truth in stuff that you theoretically always knew, but all of a sudden you see a curve that plots the scaling behavior. And the curve that I was absolutely shocked by, but knew for many years, was the curve on the scaling of variational circuit training on hardware, which scales with the number of parameters, right? So these parameter shift rules means you need 2 evaluations per parameter. Now, I always thought this was fine, right? It just scales with the number of parameters, but obviously neural networks don't. In neural networks, you can compute a gradient once. So I feel that this work is also super important because it reduces the number. So reducing the number of parameters is so important because our training depends on the number of parameters, which is not true for neural networks. So my question would be, do you have any feeling of how compressible these circuits actually are? So could you say in the end that we have, I don't know, in the near or long-term future, we've got like really deep circuits, and in the end, we just need 20 or 30 parameters? And do you think quantum circuits are different in this regard to neural networks, where we need billions of parameters for big data sets?
Yeah, so that's a great question. So I've also been thinking a bit about this idea of compressibility of quantum neural networks. And in some sense, when I was showing that data of the VQ optimization profiles of lithium hydride, where for 3 bond lengths, I ran 25 random initializations. And from that, we saw that there are many ways for this circuit called LDCA to reach an effective solution candidate by using different parameter subsets. So I think this type of analysis actually provides that additional insight that LDCA is very compressible, or there are definitely ways that we can cut down on the number of parameters. So I think after this study, what I'm interested in is actually knowing that this circuit is compressible. How do we get there? How do we find a more compact representation?
And how does it scale, right? That would be
Exactly.
super interesting also to compare machine learning and maybe quantum chemistry, because you might find very different ideas about that. We have a question from the floor that whenever you give a quantum machine learning or variation circuit talk, someone will always ask this, and it's a very good question always. What about noisy simulations? So is there a particular reason why this should be a problem here? Or
Yeah, so in some sense, the simulations I showed today are kind of in the more perfect type of scenario where it's noiseless and all the expectation values are computed exactly. But one, I think, strength of PECT is the flexibility in its implementation, where I don't assume anything about the actual optimizer that you use to tune the circuits. This is rather a framework for you to find the right parameter subsets. So you could imagine just plugging and playing with different types of optimizers that are actually aware of the quantum noise. For example, various works by Patrick Coles and his group on these like measurement frugal optimizers that takes it into account of shot noise. So those are definitely some future directions that you can explore in order to improve upon PECT. Yeah.
Nice. My next question is actually a very, very big one, and I'll formulate this a bit critically for the simple reason. So I want to ask this to anyone who does work in the field, but I picked you because I think you might have a very good insight in this. And I'll formulate this a bit critically. So whenever we use variational quantum circuits for any applications, and I'm thinking here in particular of calling them quantum neural networks, comparing them in machine learning, I sometimes find we have worked for years on this, and we've chipped away so many parts, as you showed in your slide, the optimizers, barren plateaus, how to train them, this and this. But in some sense, we still have, at least in quantum machine learning, absolutely no idea what variation circuit to use. So when you look into papers, you always find this moment where people say, oh, let me just randomly pick them. I'm asking you this because you have done work on like comparing them also systematically. But now I sometimes start wondering a bit if we are thousands of people researching with thousands of papers coming out, and we still don't know what variation circuits to pick for a problem. Aren't we in trouble? And sorry if I explained this for so long, but this is really like an important question for me. So compare this to neural networks where quantum circuits are general computations that just can do anything. Neural networks have a structure, so people have already picked it according to like developments in the brain. So we're basically just saying, do any computation and then just do something random that we can just do on hardware and do this. So what we say about this criticism, can we get out of here?
Wait, so sorry, could you repeat the question exactly?
Or like phrase it as a question. Yeah, no.
Yeah.
So my statement will be, yeah, no, actually, let me phrase this as a question. After so many years of work, do you see that we have specific pointers towards picking a variational circuit, and how can we get out of this? I know that you are very good at systematic studying things, like very carefully. How can we get out of this problem that in every paper there's this moment where it says we just pick like random entanglers and some variational gates?
Yeah, so towards that problem, I wouldn't say I know the exact solution, but the way that I'm currently thinking about it right now is, right, we, for quantum computing in the near term era, we have to be somewhat close to the hardware. So in terms of the gate types that we use in our circuits, as well as the assumed connectivity in the circuit, I think those should come exactly from the hardware that you're trying to run the quantum experiment from. And from that kind of building blocks, then you, in my opinion, you can just build like we build these quantum neural networks, build a hopefully expressive design, a circuit with high quantum expressibility. And then I would say apply a method like PECT or layer-wise training that tries to then use this template as like a very structured tool set of quantum operations, and you just chip away at the circuit in order to tailor it to solving your problem. So that's where I'm at right now.
That is a very clever answer, because you're basically saying, I don't know if people followed yesterday where we talked about quantum differentiable programming, where we said, if you don't know what's the answer, if we don't know what's our neural network structure for quantum circuits, just learn it. Just like make an algorithm that chips it away. Yeah, that's very clever. Cool. I'm happy I asked you. I want to get a bit away from technical stuff, as it has been a bit of a signature here to also like go a bit into personal opinions and study the field and the communities. And you are very involved in lots of initiatives. So I mentioned the Unitary Fund. You're very often like involved in projects about STEM and women in science. You're also like part of the Quantum Open Source Foundation. I think you're a mentor there as well. So that seems like you put a lot of your energy into creating a change and creating a good community for people. What is this community that you want to create? Are there changes that you would like to see?
I mean, how to look at this? I do think that the quantum computing community, I mean, of course, there's always ways to improve the community, but I think currently we are doing a fairly good job overall on just being inclusive, being welcoming people from all different backgrounds, and making sure encouraging them to stay in the field, which I think is huge. And there are various ways to do it. For example, like your talk with Amira today, she's someone whose social media presence really inspires and educates people, and I think that's a really amazing way to really change the way that you communicate and encourage folks to join quantum computing. Unfortunately, I don't think I have like the social media personality. I feel like I'm much more dull in that way. So at least, but I still want to contribute, right? So I think that's where I'm much better at these one-on-one mentorship or conversations that we can have. There are often times that people just reach out to me about quantum computing or quantum computing research, and I'll if I have the time, I'll try to schedule short Zoom calls with them just to talk about, you know, how to get in the field, like what's your everyday like, and just making it more welcome for everyone, really.
Is there any advice that you often have and give to people, especially if you mentor a lot? I mean, now you've got a crowd of people who you can give the advice it wants to. So
Yeah, so I personally learn best by doing small examples, either toy examples or anything small. And I think actually that's where resources like penny lane tutorials are really useful because you can run through every step that someone has already coded up for you while looking at all the descriptions and the specific papers that they refer to. So I think that's a great way to actually get started on fields like quantum computing.
Yeah, and then another advice, maybe also from I don't know, emotional side of research. I'm asking you because in my mind, Harvard and lots of the other institutions always have a specific role for me, which means they are very competitive. And I know, for example, for myself, I would never be happy at an institution that's like that because I wouldn't want to play that game. So I'm a bit interested now. So how do you deal with this thing? Do you have advice for people like that who are not yet doctors, but who are actually like doing their PhD in an environment that is hard and competitive? Should you just chill and leave it? Or
Yeah, that's a great question. And I don't think I have the perfect advice, but just from my own experience, right? I come from, so Alon's group, everyone is so smart and very like, accomplished. And especially the first couple of years of my grad school, I just felt like an imposter. I felt very insecure. I'm like, do I even belong here? These are amazing, smart people. But I think over time you realize that it's okay to not be the smartest person in in like every part of quantum computing or every part of what you're doing. The point is that you're going to school and you're working with people to learn. So I think as long as you place emphasis on the learning aspect and just I don't know, gain satisfaction from learning new things every day, I think the insecurity is never going to go away. But I think one thing that grad school taught me is to embrace that and be okay with that insecurity and just not let that get to you.
actually, on that note, one of the things that I found very helpful to understand, I only understood it last year really properly, is that we always think there's a prototype of a scientist, and we have a certain idea about what that is. Everyone has probably a different idea. And I realized there are actually very different types of scientists. So they're the ones that are chatty and communicate a lot. They're the ones that only sit down and do calculations. And they're ones that are politically super connected, but maybe they don't sit down and they've never done like the maths really properly. And all of those are actually super important. And if you start understanding that you can just find your spot and you don't have to be that one, it's actually quite liberating. I don't know. Is this something that resonates with you?
Yeah, no, definitely. And I think that actually for me that came with time. I was like so deathly afraid that, I just wouldn't find that spot, but it comes to you. Just
Are
so.
you in a position to describe what your style is, for example? So something that's your strength, kind of
Yeah,
in research, if
so
you say it's on social media, for example.
oh
But yeah.
yeah, a strength.
So
Uh,
this is not a job interview after you did your defense. I'm just like wondering. So, for example, I always like admire how you do research very, very carefully, and you build the question very, very carefully, and then you find a very simple way to phrase it and answer it. So that would be a really cool strength. Yeah.
yeah, I need to have like a very clear, like well-defined question for me to really understand it. Uh, Also, I was going to say one actually really helpful advice that I got throughout my PhD, coming back to like this idea of high pressure environment. Um, uh, One good way that I got over this like insecurity of like, am I good enough? Like, will I ever be able to generate original research ideas? So one advice I got was to actually keep like a mini notebook, which I call like an incubator notebook, and I just put down like random ideas of projects that could be possible and that could be interesting. And most of them don't actually pan out, but it still keeps your like thought process going. And eventually, sometime in the future, you're gonna look back and these ideas they might mean something different at that point, and that actually provides a lot of like interesting research ideas for the future.
That's actually a nice one. It reminds me a bit of so there's one psychological problem in this research field. Sorry, we're getting like very deep here, but we're just doing this one in a couple of minutes. But like, there's one big problem, which is that the results of your work are always like so long, so far away. You have to really trust the process for a couple of years. I mean, sometimes you even give talks before you have a paper with a result, and you don't know if you'll ever have this. And if I may venture this very briefly, I've mentioned it before sometimes, but I sometimes think that research is a bit like being a music star, pop star, where you have to, like you have to produce papers instead of songs, but you don't know how the crowd will react to them. And sometimes it takes you a year of inspiration to get a song out, and sometimes people just don't like it because in 30 years' time they might only like it. And I sometimes think that, so when I think about that, my second thought is always that a lot of pop stars and rock stars are depressive and are taking drugs. A lot of them die. And I always wonder, what is this psychological point that we are dealing with? And I sometimes wonder
Mm.
if this is like very similar.
Yeah. It's as if like papers are kind of like very clear milestones of you making progress, but I don't think that's the only way that you mark progress, right? If anything, that's like something I learned in grad school. You're not defined by your papers.
Yeah.
You're defined by the conversations you have, like the scientific insights that you share with other people and inspire. So,
Yes, and
I
if
mean, of
you
course,
are,
papers are important, but you know,
if you're honestly interested in a problem and you're honestly trying to solve it, there's probably nothing to stop you. Yeah, okay. Let's leave the slightly more deep topic. I actually wanted to ask you something about your first name because I'm always confused about it. Because in some papers you go with Sukin, and in some papers with
mm,
Hannah. So I got to know you as Hannah. And I met you actually once in Korea on a conference where you were there with your parents, because you're originally from Korea, actually from the city, I think, where we were back then in Daejeon. Oh gosh, I don't even know
yeah,
if I pronounced
yeah.
this. Cheers. And the context of my question is also because locally here in South Africa, where I am, people always have two first names, and to white people they give always the English name because they're a bit stupid and they always forget their other name. So it's more like helping them. And then to like the real friends, they always give like this other name that really defines them. Is this okay? We're
Yeah,
deep again. Anyways.
I mean, it's a great question. So my official name on all the official documents is my Korean name, Sukin, but I actually chose an English name similar to what you just stated because in elementary school, people just wouldn't either pronounce my name correctly or would make fun of the pronunciation because, children. But I think so. I had a choice in high school to actually change my official name to then include Hannah as my first name and push my Korean name to my middle name. But I ultimately decided not to because I remember when I was way younger, especially when I first came to the US when I was 8, I really struggled with my identity because at that point I didn't feel like I was American enough. But then also over time, I'm becoming more American and less Korean. So then I'm like, oh, I'm not Korean either. So I really struggled with that. But I think with age, you just become more comfortable with yourself, with your identity. And I think when I chose to just go by Sukin for my official name, that I think reflects some of that growth I had, where I'm just like, now I'm comfortable in my own skin, my identity as a Korean American, and I want to make sure I value the Korean side of my background, especially because it's the name that my grandparents gave me. That provides a lot of meaning.
Yes, and maybe it's exactly the same as in science we said earlier. There are lots of different ways you can be, and that's the same with your double identity. Probably most people are actually. Yeah.
Yeah.
Yeah, cool. My last question, let me just have a very quick look. But my last question to you would be on a bit of a lighter note to finish off. Actually, two parts. Looking back, what was the best part of your PhD? Looking forward, what's next?
Oh man, best part. I mean, definitely, I was lucky to have a lot of mentor figures and throughout my PhD. I think that was the best part. They really helped me through the various highs and lows. And actually, that also answers a second question because a lot of those mentors actually are at the company's Apollo Computing, and that's where I'm going to go next as a research scientist. Yeah,
Nice. Congratulations for that. That's amazing.
thank
Okay,
you.
great. I think we'll finish here for now. There's a couple of announcements I want to make, but first of all, thank you very much, Hannah.
Thanks, Maria.
Or Sukin. Yes, I'll switch between the two. I'll diversify the name that I address you with.